Hello everyone. Today I'm going to talk about an onboard optics based blade that we've developed for the OCP Minipack fabric switch. My name is Chris Berry and I'm an optical engineer at Facebook, and I'm in the network hardware group. This represents our first project in developing and deploying onboard optics in our data center. So, as way of outline, I'll begin the talk by giving the background and motivation for this work, and then we can talk about the hardware design and go into some of the lessons that we've learned throughout this project that we wanted to share with the community, from deployment to design, and some of the implications in developing and using onboard optics. So, in terms of background, I wanted to start off by talking a little bit about integrated optics and what this means. So, traditional optical modules are developed using a bunch of discrete optical and electrical components, and these components are then generally packaged into a module. And a large number of optical modules have been manufactured and produced this way. But in recent years, there's a lot of interest in industry to take those discrete components and integrate them into chipsets with more functions integrated into a single chipset, and to marry the electronics and the optics more closely. And so in doing this, you can do several things. One thing that this allows you to do is to reduce the overall size of the optical engine, including the electronics that drive it. And this in turn is enabling new architectures for systems and new design possibilities. So one of these is onboard optics, or sometimes abbreviated OBO. And so this is when optical modules are mounted directly on a PCB, as opposed to plugging them into the front plate of a switch with a pluggable optical module such as a QSFP or OSFP. And the other more extreme version of this is co-packaged optics, or CPO, and this is where the optical modules are actually packaged with the switch ASIC itself. And integrated optics, in any of these domains, it provides several benefits that are often cited, from power savings, improved cooling, and offering different flexibilities and enabling new designs for systems. And those are talked about a lot, and I don't want to spend too much time in that, in revisiting those. Instead, I want to talk about this specific work where we launched our first OBO project. And the goal of this was to get through an entire development cycle and learn as much about onboard optics as we could, all the way from development, deployment, manufacturing, assembly, and how these devices are actually operated in our data center, and what new challenges we face when going down a path like this. So for instance, if you have a pluggable module, those are clearly easily serviceable. And if you have a module fail, that can easily be replaced. However, with the onboard optics module, it's not as serviceable, so replacing that may cause you to replace several modules, any other modules that are integrated into a single blade, or what we sometimes call PIMs, for pluggable interface module. And there's a trade-off here, whereas when you go with integrated optics and the components are all integrated into chipsets, you expect a higher reliability rate because you have fewer discrete components, and at some point you would hope to approach the reliability of silicon electronics. However, it's not clear how this nets out in terms of RMAs, whether higher levels of integration and fewer discrete components with less operator handling gives you a better overall RMAs, versus having the ability to just replace a single port given a variety of failures that we see in data centers. So to give a bit of context in this work, I wanted to talk about where we were when we started this project. And one of the main goals was to get through an entire development cycle as quickly as possible to get to the point that we're deploying this in our production network and we can start seeing how this operates in the real world. And so to do this, we made some choices about choosing technologies that were available at the time and using that to speed up the entire development process rather than going down a fully optimized, developing a fully new switch, completely optimized for onboard optics, for example. So we're using the existing OCP Minipack chassis, which is really great platform for development. It allows us to easily integrate a completely new design into this modular chassis. And we're able to develop our project on a known good platform. And so there's a lot less development based on that, and we can focus on the parts that are different, like the onboard optics pieces. But one trade-off that you will see here is that the power savings that we'll see in the PIM, it's not going to be the full promised power savings that a completely optimized solution may give you, because we're reusing the same reverse gearbox here. We have basically the same electrical link between the ASIC and the pluggable module that we have in the regular Minipack. So a lot of the power savings that you are promised with onboard optics is by reducing the power on that electrical link. In this case, we're using the same electrical link to speed up the time to deployment and to increase the amount of learnings we can get in this first generation. In the same vein, when we were starting this project, the availability of integrated CWDM4 muxes and demuxes into the optical modules, it wasn't where it is today. And so at the time, we made the decision to go with an external CWDM4 mux and demux outside of the optics module that we then connect up through fiber. And so we have a centralized mux demux to work for all of the optical modules in the PIM. And this has this improved our time to deployment, but it came at the cost of an increased complexity in fiber routing and the design of a fiber tray to support this. And then in manufacturing and assembly, it adds complexities in this fiber management. And I'll talk a bit more about that later. And again, just to, I think I said this before, but the priority here is to get as much learning through all stages of the development cycle, including in our production network. And some of these tasks or some of these learnings that you get in a production network, they only come after a device has been operating for quite some time. So priority here is making trade-offs to improve the time to deployment. So this is a picture of the system, and it's configured as we're deploying it. So here you can see the Minipack OCP, the OCP Minipack chassis, and the outer two PIM cards on the left and here on the right. Those are the standard PIM16Q PIM cards for pluggable optics modules. And in the center here, we have our onboard optics PIMs that we call the PIM16O, O's for onboard optics blades. And we chose this configuration with both the standard PIMs and the onboard optics PIMs integrated into a single chassis for a couple reasons. One of these reasons is it gives you a literal side-by-side comparison of the pluggable PIMs versus the onboard optics PIMs when you're looking at things like failure rates or time to cable up a link and other metrics. And I should note that there's no technical reason why you couldn't install on all 8 onboard optical PIMs, and some of the results that we'll talk about today are from tests done in that configuration. It's just this is how we wanted to deploy this to begin with. So moving on to some of the system specs, you can see them listed here in this table. And in general, these are the same as the OCP Minipack chassis specs. We designed this system to operate in the same conditions and temperature range, humidity, altitude, etc. So this slide shows a comparison between the onboard optics PIM on the left versus the conventional QSFP PIM on the right. So both of these have 16 100 gig ports compliant to 100 gig CWDM4 OCP spec for the optics. And comparing the typical power consumption for the onboard optics PIM and the standard PIM with fully loaded optics, the onboard optics PIM saves like 4 watts, but they're pretty similar since in this case we're using the same gearboxes and same control plane for the PIM, so you wouldn't expect a whole lot of savings with this. As I mentioned before, if you remove the gearboxes and shorten that electrical link, you could save significantly more power. So looking at the amount of ventilation area, the size of the LC bulkhead adapter saves space and it opens up about 13% more ventilation area. We also see a 15% lower pressure drop in this design. So this allows us to reduce the fan speed by about 30% for a configuration where you're deploying all 8 onboard optics PIMs installed in the chassis, or about 10% fan speed reduction in a configuration with 4 onboard optics PIMs and for the standard PIMs. So in turn, this would save about 50 watts for a 8 onboard optic PIM chassis, or 15 watts for a chassis that was half and half. So going into the architecture of the PIM, this is a 1.6 terabit per second PIM, and it's made up of 4 400 gigabit per second OBO modules and 4 gearboxes in reverse gearbox configuration. So if we follow the path of, say, a 100 gig port, so we start with 50 gig PAM4 electrical lanes going into the gearbox, and gearbox down to 25 gig NRZ lanes going into the OBO module. So there's 4 ports per OBO module, and the output here is ribbonized fiber, and each ribbon is carrying 25 gig signaling and NRZ that is on the CWDM4 grid. And then these are connected to an external 16-channel optical MUX-DMUX, CWDM4 MUX-DMUX. And then these in turn are connected through fiber to the front panel LC ports. And for the control plane, this duplicates the OCP PIM16Q control plane. So for comparison of the 100 gig QSFPs versus 4 by 100 gig OBO module, you can see from the photo that the OBO module is much more compact than the equivalent in 100 gig CWDM4 modules. And just going kind of line by line on a comparison, you can see that this represents the same number of 100 gig ports. But one interesting thing here is the number of lasers. For the 4 100 gig CWDM4 modules, you would have 16 lasers, 1 for each wavelength, and 4 per module. In this onboard optics module, the lasers are actually split 4 ways, so you only have 4 lasers total, 1 for each wavelength. So a typical CWDM4 optical module doesn't really support loopback modes, electrical or optical. However, this one does. This is integrated enough that it can support both electrical and optical loopback. The power dissipation is slightly lower on the OBO module. The footprint, though, is about 1/4 or about 1/5 almost of the footprint of the 4 QSFP modules. And so in terms of bandwidth density, this gets you about a 5x increase, and in power density, it's also about a 4 to 5 x increase in the density of integration here. So here we show the insides of the OBO module. So these are Cisco's 4x100 gig CWDM4 OptoPHY onboard optical modules or transceivers. And they've provided a couple of pictures of these modules. So in this first one on the top, you can see the module with the top cover removed. And in the center is the SiPho chipset with fiber ribbons coming out from it. And around the chipset, you can see a PCB and some electrical components. However, other than the power supply and the microcontroller, essentially all of the functionality is in the SiPho chipset for this module, which is shown in greater detail here on the bottom. So this chipset picture shows 4 of the lasers, so one for each wavelength. And then the output of these, as I mentioned before, is split among the 4 ports. This is also integrated with the 28 nanometer electronics die that's attached via micro bumps. So for some more details about Cisco's technology, here are some publications for reference that the group has put out where they discuss things in a bit more detail, and I'd encourage you to take a look at those. As far as the module installation, I wanted to show how these are assembled and held down. So on the right is an exploded view of the assembly, and working from the bottom up, we have the host board where the module is attached to, and then here we have the LGA socket, and this is a high-speed LGA socket that sits between the module and the host board, and it provides electrical contact and placement. So the module sits directly into that, getting electrical contact, and then on top of that sits a heat sink. And this is held down with compression springs and shoulder screws that hold it tight against the PCB. In terms of the assembly inside the PIM, so here we have a picture with the module's heat sinks removed, and you can see the 4 optical modules here in the front. So in the back, there's also a row of gearboxes here shown with the heatsink still on. And then farther back, there's the SMB connector and some power pins. And then out of the front, you see ribbonized fiber extending out of the front. And this is routed to a fiber tray assembly, which sits on top of this lower level. This shows the full assembly without the top cover of the PIM, which would normally cover the top. Here you can see the fiber tray, and the fiber is routed from the OBO modules to the 16-channel CWDM4 MUX/DMUX in the back of the picture. The fiber from each of the OBO modules is managed in a separate fiber spool, and it is spliced to the fiber of the MUX/DMUX. In the front, there's also fiber racetracks for the common port fibers, which then drop down and they attach to the LC connectors at the front of the PIM. So as you can see, one of the trade-offs that I mentioned earlier about going with the external MUX/DMUX, so although it sped up time to get the project deployed, it definitely increased challenges in fiber routing and manufacturing. And this is something where in the future generations, having the MUX/DMUX integrated inside the module, that would clearly significantly simplify the PIM assembly and design. So looking at the front panel design in a bit more detail, you probably notice that the LC connectors are here oriented on a 45-degree angle. So this improves serviceability to the PIM and increases the amount of space between ports so larger fingers can install and remove the fibers. Although the front of the connector is compatible with standard LC fibers, the back of the connector is a micro LC connector, which is quite a bit smaller, and this saves space inside the PIM. And the bulkhead adapters are also metallized to meet EMC regulations. And as I mentioned earlier, there's about 13% more ventilation area in this design than the standard PIM. Next, we wanted to talk about some of the things that we learned during this project. And the first one is something that we're still trying to collect more data on, and this will inform our future designs. The clear difference in going with an onboard optics-based switch is that the ability to service optics in the field is decreased. So for example, if you had even a single of the 16 ports fail, this could cause the full PIM to be R-made. And in any optical module, the most common hard failure is a laser failing. And since the OBO module shares one laser between 4 ports, a laser failing would actually take down 4 ports. So this means if we see just a single port go down, it's really more likely that, in this case, that either it's a cleaning issue, an issue with the other end of the link, or something not really related to the optics. So all of these reasons for serviceability, it also increases the desire to improve the ability to inspect and debug a port if it goes down. So the last thing to note here is that in future designs, high-density dust-resilient connectors could be interesting as we're flexible in the design of these PIMs to do that and open up more front panel space for ventilation and reduce the sensitivity to dust. And as I've mentioned in a couple ways differently, the ability to debug onboard optics becomes increasingly important due to the increased barrier in servicing them. So the ability to initiate electrical and optical loopback modes within the module can really help to isolate sources of issues. And the ability to upgrade a module's firmware in the switch is increasingly more important. And I wanted to note that these features are useful, and we found them useful for both manufacturing these PIMs and for when they're used inside the data center in a real environment. In terms of changes to software, with 4 ports integrated into each optics module, it breaks the assumption of one port corresponds to one module. Additionally, it becomes less clear if a port is cabled up from software. And what I mean by this is, for instance, with the pluggable module, you can make the assumption that if a module is installed and detected via the presence pin or through I2C access, that the port is cabled up and it should come up. With the onboard optics module, the module itself is always there, and there's not a good way to tell from software if a given port has fiber connected to it. So you have the RX loss of signal, which will detect light, but it might be asserted for different reasons than a cable not being there. And you don't really have the same way to detect if a link is installed as expected. So in terms of network upgrades, the standard PIM16Q, it uses a reverse gearbox, which allows 16 100 gig ports to be operated, or you could operate it in a mode with 8 200 gig ports. So this feature adds some amount of flexibility when you're thinking about staging network upgrades between generations in your hardware. And this wasn't designed into the onboard optics PIM, but it could be interesting for future designs to also have that flexibility. I could keep going here, but I think this is one of the last ones we have in this presentation. With the construction of these PIMs changing, the tricks to meet EMC standards change a bit. For example, to help with this, we use metallized LC connectors on the front panel to avoid large electrically open holes on the front panel. Additionally, the heat sinks extend past the surface of the module a bit, so you can apply RF absorbers in this region to help with emissions. And then finally, you can ground the heatsink, which will also help. So in conclusion, we wanted to talk about Facebook's first onboard optics program, which is still ongoing, and we're trying to learn more about how these platforms perform in our data center environment. We'll take the lessons we learned here and apply to future generations and try to share our findings with the community. We're also open to releasing the design of this PIM to OCP if there's community interest. I wanted to thank everyone who has contributed to this project. I'm just one member of a large team, and this team has worked hard to get this project to where we are today. integrating onboard optics into a switch really brings in people from a bunch of different fields, from electrical, mechanical, thermal, optics, software, data center teams, sourcing, and on and on. And I just want to thank everyone that's worked on this. And then finally, I want to thank the companies that we've worked with that have made this possible. And we've had some great partnerships in this project, and thank you very much. And finally, I want to wrap up by saying that onboard optics and co-packaged optics continue. And you may have heard that Facebook and Microsoft have partnered for joint guidance documents for co-packaged optics. So we're looking for active industry feedback and participation to join in and to help us shape this. So here's a couple links to the project and guidance documents. And this is a long path, and we could use everyone's participation. Thank you very much.
Hi, everyone. Thanks for joining in. We only have a couple minutes for questions, but I wanted to cover a couple of the questions that came in at the end. So Ali asked a question about power savings on this, and I think he's picking up a key point that the entire reason for doing this is that we see if we continue the same trend line for the next several generations of switch bandwidth doubling, eventually we're going to hit a power limit of based on our facility limits. And so a portion of this effort is to learn how to build switches and embedded optics. However, here we were trying to prioritize time to deployment, because an even larger goal of this is to learn how to deploy these solutions in our network. So this includes not only the initial installation, cabling, provisioning, but also how we service these once they're deployed. And it involves building up tools to debug the potential issues and learning about the operational issues that we face when we're trying to service these. And the hope here is to learn how to improve all these areas in the future, knowing that there's definitely some power savings left on the table by reusing existing chassis platform and gearbox and electrical link between the optics and the gearbox. I think there was also a question on manufacturing testing and reliability. So this has definitely been a very different manufacturing case than the normal switches, because here we have the optics going in to a traditionally electronic platform. And so you do have more testing in the optics and a little bit more assembly at manufacturing time. One of the things to note here is the fiber routing and splicing. That was a challenge in manufacturing to deal with the splicing and routing. Definitely manageable, but that's something that's not inherent to onboard optics. That was just part of this design in order to, again, get to deployment quickly. So in the future, manufacturing can be greatly reduced by embedding the MUX and DMUX into the onboard optics module. I think that's about all the questions I see, and we're about out of time. So I wanted to thank everyone for joining, and hope you have a great day.